All right, here we've got a three-part question, essentially about this sampling distribution and how it's constructed. And here you see we're talking about the sampling distribution of the differences in the means in two different groups. I'll let you pause the video and read the context if you'd like. Um, but we're going to go ahead and move forward and answer question A. What is the shape of this sampling distribution of the differences of the means? In this particular case, we're talking about the cholesterol levels of men aged 20 to 34 and comparing that to the cholesterol levels of 14-year-old boys. So the shape of the sampling distribution. So this is really referring to one of our conditions. One of our conditions is that our sample size is big enough that we can approximate it with the normal model. So usually we're checking this condition. So this would be for the men, this would be for the boys. And in this case, you see this, one of these actually fails this condition. But the whole point to checking this condition is to say that if our sample sizes get 30 or larger, we can estimate this distribution, or it's going to be approximately normal. Okay, so if we know that we have a normal distribution to start with, then we're okay. We don't necessarily need sample sizes of 30. So if we look up here into the context, we've got normal distribution for the men, for all men. So this one actually checks out. It's not bigger than 30, but it actually checks out because it's normal. And blood cholesterol levels for 14-year-old boys also fine, follow a normal distribution. So the shape is normal. And the reason is because both sample distributions individually are approximately normal. All right, so moving on to part B here, find the mean of the sampling distribution. Remember, this is the sampling distribution of the differences in level of cholesterol in the males and or the men, and level of cholesterol, average level of cholesterol in the boys. So in order to find that mean, mu sub x bar of the males minus x bar of the boys, or in other words, the mean of the sampling distribution of differences in means between the men and the boys. We just take the two individual sample means. So we've got 188 for the men and 170 for the 14-year-olds. And this distribution of differences, sampling distribution of differences between the two, is just simply the difference between that. All right, so we know that this distribution is centered at 17 milligrams per deciliter. And now we need to figure out what the spread or the standard deviation of the sampling distribution is going to be. So we are dealing with the sigma or standard deviation of x bar for the males minus the x bar for the boys, or the standard deviation of the sampling distribution of the differences between these two. It's a mouthful for you. The way that I find this is I always add the variances. I add the variances when I'm combining different distributions, whether I'm adding or subtracting different distributions. So square root, because it's the standard deviation, and I want the variance of my first distribution, which is the males. So I take the standard deviation squared, which is 41 squared, and I divide it by however many there were. And so in this case, we go back up here and we see that these are SRSs, independent SRSs of 25 men. So there's my sample size for the men. And I add the standard deviation of the boys here. Oh, that's the mean. Sorry, the boys is 30. And notice these are population standard deviations. These are not sample standard deviations. So my formula, I'm literally putting sigma squared over the n for my first group, and sigma squared for the population standard deviation over the sample size for my second group, and this is my formula. Okay, so let me see. SRS of 25 men aged 20 to 34 and 36 boys. So I got 36 here. Go through a little bit of calculator work and you should get approximately 9.06 milligrams per deciliter. So we now know that our sampling distribution of the differences here is centered at 17 milligrams per deciliter and has a standard deviation of 9.06.